My name is Evgeny. I work in Rails Reactor. Here's my links to my social blah 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 something. And here is the link to this presentation. So if you want to open it on your laptops or phones, it's about the time. Okay, so what is the topic of my talk? I mean, the title is very broad, very huge. So I try to narrow it down to some really specific problem, and the specific problem is to have some fun out of functional programming and animations. So my talk, small disclaimer, my talk is heavily inspired by this book. It's written by Paul Hudak. It's about, in general, functional programming with multimedia or multimedia with functional programming. And specifically, I will talk about animations and also a few words that Paul Hudak and Connell Elliott about 20 years ago came up with a nice idea about functional reactive programming, and the idea of functional reactive programming was born out of some functional reactive animation. So it's just usual animation but interactive. You can click, move your mouse, and the animation will somehow react on your inputs. And 20 years ago, that was like not a huge, but nice. So what I'm trying to solve, I'm trying to do something like that. No interactive animations today, just some regular. And I start with some, I don't know, some pretty basic sprite animation with help of Doom Guy. And this is what I usually do when I try to do something with Canvas. As you can see, there is a lot of boilerplate code. There is a request animation frame and callback loop, and you also see that there is some rules for my animations, some periodic functions, some I don't know, lookup into sprites array. So it's pretty imperative, but it's not bad. It works, and it looks something like this. But the thing is that it's not enough for me. Like, yeah, it works, but then I want to try something else, experiment a little bit, maybe slow animation down, or maybe change some parameter here and there, and I don't want to lose this one. This works perfectly fine, so I start to copy and paste, and those animation functions, they will grow in their number, and the problem is that with small changes like here, you will have to copy all this boilerplate, and that would be nice to have something like this to describe your animations. Just some methods maybe where you specify some parameters, and that's it. So the Canvas API is hidden somewhere in this class. It's abstracted, and you just describe what you want, and then maybe you run it or maybe not. Yeah, so we will do something like that in this talk, and we'll start to abstract. So the first step is to like split everything, move, like separate, decompose your function, animation function, and this is what you probably came up as a first step in your decomposition process. Is this really functional programming? Well, not. Even though you define some functions which do some small bit of work, there are a lot of problems with that. The main problem is you still call methods API methods of Canvas inside your functions. Why is bad? Because you know, when you want to try to compose those functions, that means that you basically run them when you call them. So you cannot really defer the animation when you specify, when you describe something. So for example here, if you don't want to run it for now, you just can specify this one part and maybe compose with another animation, and it doesn't really run before you tell. So with this this approach, that would be problematic, the deferring of this execution. So also when you try to, I don't know, when you start experiment, you start with some crazy ideas. What about I want to render it into GIFs or GIFs, or you want to try different environments. You heard that Skia was ported in WebAssembly, so this API also is enabled in your browser. What if you want to create a live coding experience inside your console? So how to do that? And that means that you really have to separate the description of your API and its execution. So here we came up to the idea that to run this code, to run this translate, draw image, and clear rect functions, we need some probably optimized, probably not runtime, but we will pass only the resulting animation description or declaration, and our declarations will live somewhere else. So how to do that? We'll start design with data type. So we start with here, for example, I use TypeScript. You can also use Flow, but also JavaScript will fit into this idea very nicely. So you have to start your design of your API with data types. So I mean, it's a good approach to start defining types before you actually start to implement something. It would be easy then to use it, because after your implementation is done, you don't have to create any declarations, any annotations. It's already done. So there is nothing to cover with types. It's already was covered with types. So it's nice benefit to start the design of your application, of your functions, with data types in mind. And we're gonna start with some very specific and atomic actions of our API, graphic actions. So for now, nothing related to animations directly. We just specify some basic actions we want to do with our graphic API to render some static images. So here you can see there is move, scale, object types, and types of objects, draw image, empty action, compose action, what it is, why we use the union type. So this basically is known as discriminated union, means that we have some very broad type which correspond to some concept like graphic action, some action with Canvas API, for example, and it actually can take values of different very specific types. So for example, the move type will contain the information about coordinates, and scale type will contain not type, value of this type will contain the scale factor. Draw image will have some information about sprites. I don't know, it might be some name or reference to resource manager. It depends on you, on your runtime. And empty action and compose action, it's to like helper things that will help you to compose those actions. So the idea is that first of all, from those specific actions, you can compose some kind of tree, some nested structure, and it will also have a graphic action type. Why we do that? Because for our runtime, we will have to parse this structure back. And yeah, so this will look like this. Here you see some imperative, right, API of Canvas, and this is how it can be presented with those types. So looks like some abstract syntax tree, I don't know. And yeah, after that, what we have to do, how we can work with those types, we will define our functions, finally, like move, scale, draw image, and what they will do, they will just construct the values of some particular types in this graphic action union type. So if you remember on previous slides, there were directly canvas methods calls, and here we just return the values of graphic action type. And one of the interesting functions for me is this and then, which allows you to compose your actions. So using this function, passing values of another graphic action, you can compose. And this is nice, I think. So how our runtime will work. So runtime is just a function which try to match the animation value, no, not an animation, graphic action value, and it tries to check its type, and it will handle it differently. So depending on the type of the object, we can perform some actions, and then just run it. Run graphic, pass some canvas context if you need it, and this is our program. This is what our declaration. This variable contains our declarations. So, animations. How we can define the animation? Also, we can think a little bit about what the essence of animation might be, and in terms of graphic actions. So it's just a series of graphic actions which happens over some time. So basically it's just a function which gets the time and returns type graphic action, for example. Time is just a integer, just number for now. And yeah, this is the interface of this animation type, and this is generic type, as you can see, and it doesn't explicitly say that animation function should return graphic action type. It was done so we can create different kind of animations. For example, we can animate the change of some numeric value. So it's not really an action, it's more like, you know, like a signal in I don't know, in physics. And this is actually represents this idea why we should even concern about it. Also because we want to change over time some parameters of our moving or scale action. So this is done for those purposes. And we don't need to modify our previously defined run graphic, because we will extend the context of our runtime with animation. So we will define another function, run animation, and that's just it. We just put it inside the loop function, which we defined on the first one of the first slides. But you can clearly see that first of all, it's much nicer, and also you can see that there are no specific to our animation logic. So you just pass the animation, you run its composed function, and as a result you just get the type graphic action, whether it would be the draw image or compose action with draw image and moving. We don't care. The run graphic will parse this value for us and do something in a canvas. So we cannot use, obviously, the functions defined for graphic actions. We need to define our own scale, move, draw image functions to operate on animation type. And there are two ways how we can do it. We can specify for each corresponding function defined graphic action type and return the corresponding animation. Or we can use some helper functions which will do this for us kind of automatically. So this is called lifting, and this is how it actually looks. So pretty generic function with which gets some function from, I don't know, A to B, and some already constructed animation value and return as a result another animation. So basically the same as we define for a function scale A, but more generic. So we don't need to specify like 10 functions. We just use only a couple of them, and then we kind of lift our simple functions to the functions which operates on animations. That's easy, I think. And how to use it? So the same way as we used for graphic actions, we just call those already lifted functions. And also the nice thing is that it's also kind of deferred. So this animation is already defined. We created this tree of objects, but we didn't run anything. And we also can even improve our code. If you can call this improvement, we can hide some of this stuff inside animation library class and provide it with chaining. So basically, the chain would be the same as and then function, which will compose the animation returned by this method and animation defined here, and also returns the animation, and also we can again compose it with scale, and that's basically it. And after that, just run it when you want. So I don't know, it's pretty nice. I mean, it's way better than we defined it on the previous slides. So there is also a nice thing that some of those abstractions they can be reused even in different contexts. So for example, yeah, I saw recently an article with a guy who animated emoji in address bar, and I tried to do the same using the approach I described earlier. So I defined also my time emoji action, which just has a single character and composed character. I didn't add all the code here, so just believe me that there are also defined functions to construct values of those types, and there is the runtime for it, which will parse every single emoji action or transform, and we'll run it, and the action just, I don't know, append to location hash. So the animation will look something like this, and this is how it will define it. Yeah, this is I think it. This is what I wanted to share with you. So a little reading list, Haskell School of Expression, original paper about functional reactive programming, and a few inspiring things just to maybe if you're interested to dig into functional programming. Thank you.